All right, good afternoon, everyone. We would like to begin today's seminar by acknowledging the people of the land that we're standing and working from. So in Canberra, it's the Ngunnawal and Ngambri people, and we pay our respects to the elders, past, present, and emerging. So today, we're very glad to truly have a hybrid seminar, where in person we have Sarah Kasovich joining us, will be speaking to us right here, and just a little bit of introduction about her. She holds her first class Bachelor of Science degree with honors in geology from the University of Wollongong, and went on to do her PhD in micropaleontology, specializing in radiolarian taxonomy from the University of Queensland. Since graduating from her PhD, she joined the JOIDES Resolution as a science operator at Texas A&M University, and in October 2021, she officially accepted the position here at ANU as ANZIC program manager, and they came here finally just a few weeks ago. And we're very happy to have here to speak to us today. And also joining us online in 20 minutes, I was told, that it will be the outreach officer, Maryalice Yakutchik and Dr. Derya Gürer from the boat itself, which Sarah will tell us where the boat is in a bit. So a little bit more about Dr. Derya. She did her undergraduate in Bonn, Germany, master's in Oslo, Norway, and PhD in tectonics and geodynamics at the University of Utrecht, Netherlands. And she joined the School of Earth and Environmental Sciences at UQ in August 2018 as a lecturer in Earth Sciences. And for August 2021 to this year, May, she'll be here in RSES as research fellow, working closely with Dr. David Heslop and Andrew Roberts as part of the ARSES project, a new generation of paleomagnetic statistics. So without further ado, let us welcome Sarah and Mohole.
Thank you for convening. So today I'm going to talk to you about the discovering the Earth's deepest secrets through scientific ocean drilling. So first, I'd like to do my own acknowledgement and pay my respect to the traditional custodians of the land which we meet, the Ngunnawal people. I extend that respect to the elders, past, present, and to other Indigenous people who are present today. Many of us are very deeply saddened by the recent passing of the ANZIC director, Professor Leanne Anand. Leanne was a deeply inspiring leader that made incredible contributions, not only to advancing diatom research, but also supporting women in STEM. So Kelly, on the chat in the Zoom, for you guys online, just leave a chat, and Kelly's posted two things. There's one of the obituary, and one is Xavier's Costa talk that celebrates Leanne's scientific career. So a quick overview. Many of you, I'm very new to ANU. I wanted to do a quick self-introduction, and then I'll tell some stories of the legacy of scientific ocean drilling. And then a few of the accomplishments of the program. There's a 55-year-old program, so there is many. So we'll just touch on a few. And then I'll explain about the ANZIC forum and some opportunities, how you can get involved. And then we'll also connect with the JR, where our own ANU, Derya, is out there for IODP Expedition 392. So where she is, she's off the coast of Africa, just down here, south of near Cape Town. They are chasing away from a storm, so they won't be showing us outside. They probably will just stay on the bridge, but they do have stable enough connection to actually connect with us. And I'm actually very excited to connect with the ship because she's actually sailing with my old crew. And as you can see, when you sail with the crew, you become family. I'm there with a outlandish outfit right there. If I ever got thrown overboard, I would be easy to be spotted. Everyone who wears black would just disappear. Just hide this, sorry. There we go. So ANZIC, so I'm the program manager for Australia and New Zealand into this international program. There are 22 nations and there are 20 institutes in Australia and New Zealand. So as you can see, there are some holes. We've got 2 calls out right now, one for the director and one for a communications officer. The director call has been closed, but the communications officer is still open. I just wanted to do a big shout out to the ANZIC support structure to help us get through this difficult time in transition, especially Steve Evans and Kelly. So about me, I'm a Radiolarian Biostratigrapher, and in plain English, I'm a timekeeper of the Earth's history. And to a scientist, timing is everything. And I just wanted to point out that radiolarians have existed for 500 million years in the fossil record. That's much longer than some of our other favorite macrofossils like diatom. So now I want to show you the scale of radiolarians. Oh, sorry. So radiolarians are they're single-celled organisms with glass skeletons. So just keep that in mind. And now I want everyone to pull up their sleeve. I can see you all, guys. And look at just one hair on your arm. And make a note of the width of your hair. Because I've imaged these radiolarians from the Indian Ocean with one of my hairs, and that's the size of a radiolarian. So they're quite small. And over here are the cores that they came from. And the core is about 8 centimeters wide. The core is here, so if you need a reference. So I can go take a little sample, put some rads on a slide and put it in section. I can find thousands of fossils. So that's very different how the macropaleontologists work, how they spend months looking at just one bone or one fossil, and I see thousands every day. So my PhD was around problems in radiolarian biostratigraphy, in particular the Paleozoic. So in the Paleozoic, they're mostly spherical forms. And to identify them, you need to see their internal features. So in the modern radiolarians, in the Cenozoic and the sediments, they've got beautiful glass skeletons. You shine a light through it and you can see their internal features, make a great identification. But in the Paleozoic, as soon as you get sediment and you lithify it, you turn it into a rock, you actually squeeze water out of the skeleton and it goes opaque. You can no longer shine a light and see inside. You need to just look at the surface topography and you need to break it. So my PhD was about micro-CTing tiny radiolarians. So a CT is like a CAT scan for something the width of your hair. So it was quite a challenge, quite a feat. This radiolarian here is my little poster boy. He is 480 million years old. So perfect preservation for something so old. And what I've done there, I've digitally sectioned it and you can see multiple spheres. So that little red microsphere was the first time I've ever seen that in that species. So quite simple. The progress of the field is nice. So now we're going to talk about the legacy of scientific ocean drilling, but we're not going to stray too far away from radiolarians. I wanted to do a little tribute to William Riedel, who sadly passed away in 2020, peacefully in his home in Barossa Valley. So as you can see, he has a link to that drilling program, but I'll explain it later. So first, he is an alumni from the University of Adelaide, and his mentor was Sir Douglas Mawson. And Mawson really helped Riedel go into paleontology and then into radiolarians when he was trying to decide what to do after he graduated. And this was all because Mawson came back from the Antarctic and he had a bunch of sediment and he found radiolarians in them. And he was trying to find someone to study them, but there was no one out there. So he told William, you should look into radiolarians. So William did. He went off to Sweden, then off to the US, where he stayed for 50 years. So we're going to come back to Billy in a bit, but we're going to look at my favorite story about the birth of the program. So Project Mohole. And Vox magazine had a great title, which I love. It's a failed 1960s expedition that revolutionized the earth sciences. So what they were trying to do, they were trying to drill this Mohole, which is the zone between Earth's solid crust and mantle, where the density shifts dramatically. So here's a section through the Earth. This is land and this is ocean, and that yellow line, so you can see it's quite deep under the continent, so it's very shallow in the oceans. So it makes sense to go out there and drill for it. And again, I just wanted to explain sort of how this all began to understand the true story of scientific ocean drilling. This all came about with an informal group of the Miscellaneous American Society, also known as the Drinking Club. So they all got together for wine breakfasts by the ocean, and they devised this plan to drill the Mohole. And I really wanted to show this quote that came from that meeting from Henry Hess, Multimont was there. And it really rings true for the program and how it's come. So perhaps it's true that we won't find out as much about the Earth's interior from one hole as we hoped. To those who raise that objection, I say, if there is not a first hole, there cannot be a second, a 10th, or a 100th. We must make a beginning. And true to that would maybe many thousands of holes. So a couple of years later, they got some money, they figured out how to keep the ship stable, and they went and drilled for the Mohole in the Gulf of Mexico. So this is the expedition here on board, and as you can see, a familiar face, the co-chief, the chief scientist, that's only one, is no other than William Riedel, the Aussie scientist, here and here, and right next to him is John Steinbeck, the Nobel Prize winner and famous author. So they drilled, but they only got to basement. But that was still such a success for the program that there was a personal letter of congratulations from President Kennedy. And many years later, his daughter Ashley, Caroline Kennedy, visited the JR when it was in the JOIDES Resolution, what we're going to connect to in Japan in 2014. So after this, they still tried to chase the Mohole, but it wasn't the right timing for the program, and they actually lost funding. But because plate tectonics was on a rise back in the 60s, they shifted their focus, and the program really was able to take off. So in 1968, the program was properly birthed. And they went out to the Atlantic Ocean to see the mid-ocean ridge, and they wanted to drill either side. Very simple, just to prove that the ages and the seafloor, the sediment actually changed depth with distance away from that ridge. So that's actually from that first drill. So that's quite significant, but it has more significance, this story, because in exactly 1 week, the JR is going to start its next expedition, which will go back to the Mid-Atlantic Ridge, back to these sites, and actually fill in that critical gap with sampling, because our drilling has come a long way since then, in 50 years. They're actually going to go out. Even though we don't have an ANZIC scientist out there, I'm very proud to say we do have an Australian out there. She's the outreach officer, Marlo Garnsworthy. So please follow along with her. So how do you measure all these accomplishments into one tiny little talk? There was this amazing paper by the JRSO Publications Office in 2020. So I just wanted to show 2 figures from that. And in 55 years of scientific ocean drilling, there has been over 275 expeditions, over 38,542 publications, much more because this was a 2020 model. Just wanted to point out that there's been over 300 nature papers, over 200 science papers, and over 700 Earth and planetary science letters. So each one is a huge discovery. So the other figure I just wanted to pull from that paper is, this is just the ranges between 2003 and 2020, is the collaboration. So using those papers, so the size of the bubble of each country is how many publications that country has had. So here's Australia in pink, and New Zealand is in pink as well. And the line, the width of the line is how many publications for that particular country. So you can see what a collaboration that. Even Australia has so much work going on. US obviously is the leader here, but we've had major collab. It disappears. And just the last bit, the table there breaks it out again, and it breaks it out into Australia and New Zealand. So like this thing's gonna come up. So you can see we've had about 4,000 papers, New Zealand 1,000, and that's the total. So that's about 11%, over 11% of all IODP papers have come from Australia and New Zealand. That's quite huge considering our contribution, our membership. Okay, so we're very collaborative, but we're also collaborative with other programs as well. So I just wanted to highlight this one expedition. So this is a collaboration between the International Ocean Discovery Program, which I'm talking about, and the International Continental Drilling Program. So this is Expedition 364, the drilling the Chicxulub impact crater. So that's the impact crater that's been linked to the dinosaurs extinction. So this expedition has helped us understand planetary evolution and mass extinction, but it's also helped end the debate over how the Chicxulub crater formed in the minutes following the colossal collision. So here you can see the big asteroid coming to Earth. The Chicxulub crater is on the Yucatan Peninsula. There's the United States, there's Mexico. And as you can sort of see, you can't see it from the top of, from the bathymetry, and it's half on land. This is the drilling rig, so it's actually a raised platform, so we can't get the ship out there. This is actually the Chicxulub, oh wait, that's the way. Chicxulub crater, so you can only see it when you do gravity anomaly, and it really pops out. So you can see the center, you can see some peak rings, and that's the significant thing. So I just want to do this and just again. So here's a peak ring. So you get these in large impact craters, and this is the moon. So you get them not just on Earth, you also get them on Venus and Mercury. So studying this perfect impact crater, we're going to make assumptions of planetary science. So what was the peak ring made out of? This was a major question going into this expedition. And the core comes up at about 9 meters, 10 meters kind of levels. And the scientists looked at the bottom as soon as they got to the peak ring, and they saw this pink granite. And before they even split the core, they had written their science paper. That was how significant that was. And there's many other things so significant about this pink granite. Like it's got 10% porosity, which, you know, from your countertops, like water doesn't go through, 10% is unheard of. And there's implications of life and whatnot. And this, I love this model too. So these results suggest that the asteroid impact was so powerful it shocked the rocks deep in the Earth crust and caused them to shoot up before collapsing down to the Earth's surface through some peak rings. So I'm going to play this model. Put this up. Yeah, there we go. So this is the impact crater coming on. We're seeing a section of this impact crater. So this is like the limestone, the sediments on the seafloor. This is the crust, and this is the mantle. And this is in kilometers the scale here. So it's going to collide and take a look at the seconds. So I'm just going to stop and pause. So within 14 seconds, there was a 30-kilometer hole in the Earth. That's like from here to Lake George, 30 kilometers. But also look up here. There's also a 20-kilometer high mountain. Mount Everest is only 9 kilometers high. This is twice the size in 14 seconds. And then to play it, it goes up, it rebounds. This mountain collapses. This comes up, and these deep rocks come to the surface, that pink granite. I'm just gonna stub it right there. So this is the peak ring here, the formation. This is the rocks, as you can see the lines are being squished out. That's the pink granite's gone all the way up to the top. It's 30 kilometers down. It's being brought to the surface. And that's all within 5 minutes. So 10 seconds, giant hole, mountain twice the size of Everest, all comes crashing down within 5 minutes. Okay, just because it's time, I'll come back to the rest of my talk. There's only 2 more slides. But stop sharing screen. We're just going to connect to the JR because someone's got to go to a meeting. JR, are you on? There they are. Hello.
Hi, Sarah.
Hi, Sarah.
Hi, Anu.
Good to see you again.
Hi. G'day.
Yay.
Hey. Yeah, greetings from the JR. For us, it's early in the morning, 7:20 in the morning. So Glenn, he is our onboard tool pusher.
Hi, guys. So I work for the vessel owner. IODP, the science community, are our clients. And it's my role on board the JR to oversee the drilling operations. We liaise with the scientists and IODP. They tell us where the rocks are and where they want to get to. And it's my job to help work out how to get there safely and efficiently and get as much of those rocks or sediments back for you guys as possible.
Yeah. So currently we're on transit back to our site, onto our last site of this expedition, 392. And we had some foul weather, so we've not been drilling for a few days. And Glenn is going to make sure that we're going to get back safe and resume drilling operations.
Yeah, so we just headed north and then west around the top of a storm that was going to be over the site we want to be at. And we literally in the last hour just made a turn again. We're around the worst of the storm and we're heading back to site now. So hopefully we'll get a couple of days of hard rock drilling in, get some basalt cores back for the scientists, and then it's back home for all of us, back into port on the 7th of April into Cape Town.
All right, so I'll let you run off.
Thank you guys. Sorry I can't stay long.
Thanks, Len.
Yeah, and then thank you, Len. All right, so yeah, we're here on the JR. It's day 52. I am Derya. I'm a research fellow at the Research School of Earth Sciences at ANU, and I'm sailing as the ANZIC representative on this expedition 392 Agulhas Plateau Cretaceous Climate. So the Agulhas Plateau is a submerged region just down south of the Cape of Good Hope. We've been surveying this region and have been drilling at several locations into this plateau. It's thought to be a part of a large igneous province, so an ancient system, volcanic system that has been in place when in the late Cretaceous, when Africa, Australia, and Antarctica used to be closer together. So when Gondwana land was still together, or in the early stages of continental breakup, this plateau was in place. And if we look at the map here of the world, and you see the ocean bathymetry here, you can see all these dots, and these dots correspond to drill sites, IODP drill sites, and earlier programs since the 60s. So IODP project, the Ocean Drilling Program, as well as the Integrated Ocean Drilling Program, have been drilling marine cores throughout the world since the 60s. And they've been doing this on a number of vessels, and the iconic one is the JOIDES Resolution that we're on currently. It's a drill vessel that is around about 145 meters long. It's got a derrick that is about 60 meters high, which we won't be able to show you today because it's really, really early. As Glenn just said, we are in a storm, but we might peek out and have a look at through the window. So what we'll do now is to take you through the different stations of the ship, and mainly focus on the core lab. That's where the samples come up, and that's where the scientists describe and archive the cores. So let's go downstairs, and maybe we can also have a quick look at the catwalk. That's where the cores first arrive, if it's safe to do so. Yeah, let's go down. Which way do we go down?
So you can see them moving. They're not actually just holding the camera in front of you, it's actually moving. That's like Derya's arms on the wall. So it's quite high seas out there. Oh, my old one. So you saw from that map all those dots, it's like Swiss cheese.
So now we're in the heart of the ship on the core deck. I hope nobody gets seasick. It's a bit rolly today. Let's try the quick catwalk first. So usually when we go out, we put on a helmet, and so safety first. We put on our glasses, and then open one of these watertight doors to get to the catwalk.
They don't normally have those.
So where we are at the moment. Sarah, can you hear us okay?
Yeah, we can hear you.
Okay, perfect. So it's quiet right now because we haven't been coring for a few days. But when we're coring, the core actually comes up here in pipes. So now you see the drill floor. And what you see is some of the drillers are still working on the deck. So basically the ship operates 24 hours a day. So science never sleeps really. And that's the peak of the catwalk. And then you see out here, we also have Maryalice, our outreach officer, who's joining us on this 62-day expedition. So what happens is when the core comes up, we get it here on the catwalk, and then the technicians place it on this table, and then the core comes up in these liners here that you see down there, and the liners are cut into 1.5 meter long sections. Just to quickly show you also what our bits look like. So this is the bits that we drill with. That's attached to the drill string that at the moment, all the piping is up because we're not drilling, but usually those are attached, and then you can see the drill motion round about there attached to this collar there. And as you see, we have some higher sea state today, not as bad as in the last days. Yeah, so that's what happens here out at the catwalk. This is where the cores are also capped. So one side is always capped with a blue cap, the upside, and then the other side is capped with gray or yellow cap, depending on the types of samples scientists take. And then they enter the inside of the ship. We've got lots of technicians. We are on a 24-hour schedule. So we worked 12-hour shifts, each team. So when the cores come in here, they equilibrate in this box. And then the next thing is we analyze different physical properties of the cores. The first thing is that happens is to measure the natural gamma ray radiation of the cores. So each core, before it is split, is put onto this into this machine, and then the physical properties team works on the data. Then we go into this cutting room where the core is put onto this saw and split into halves. So this is where the core is split, and it depends on how long this takes. Depends, of course, whether we have sediments or hard rock. So it's split exactly into two halves. One will be the working half, the other half will be the archive half. So we always have two more or less identical copies. Then we have a number of equipment, saws that are used for discrete sample cutting, for paleomagnetic analyses, but also for the hard rock people that do make thin sections, for example. And as you see, we're a really, really big team. So our science party up here, then the ships, so seams crew, our galley staff that take care of our food and that we're doing well, and our rooms are clean and our washing is washed, and then we have our technicians on board as well. So what we have here is our last site that we recovered just a couple of days ago before the storm started. And what's really exciting about the site is actually that we have sediments. And so these sediments are limestones, and they overlie pillow basalts. So I'll just quickly show you what a pillow basalt looks like. It's basically a basalt that has erupted in water. And when the basalt cools, it then makes this rim that you see here. So it's this glass rim that is due to cooling. So that's our pillow basalt. And then we have basaltic rocks that are dark in color. And then they have these calcite veins running through them. So this was the material that we got at the last site. And more frequently, as we enter the seabed, so the vessel can draw up to 6,000 meters water depth, and different depths below the sea level, the ocean surface. And what we have here at one of the sites is some black shales that we recovered. So really quite finely laminated black shales. And then we sometimes get these unconsolidated sediments at the top, so sandy. And then micropaleontologists can look at these materials and give us an age. The paleomagnetists will take their discrete samples to run paleomagnetic analyses. And the core description team that I'm part of will be describing the core, and then then we will record each core and say exactly what interval is what in terms of the macroscopic description. and the biostratigraphers will give us ages for each of the units. Yeah, let's have a quick look into the different stations that happen after the core is split and described. This is the paleomag corner. This is usually when we're not transiting or in a storm. This is where the paleomagnetic team sits and measures discrete samples. And what they're trying to do in this case is to tease out from these rocks that we're recovering. So depth equals to time. And time is divided into periods with normal polarities. Black stands for normal magnetic polarity, and white stands for reverse. And with time, that changes. And that is because the Earth's magnetic field, sometimes the North Pole is the North Pole, North geomagnetic pole, and vice versa. And using this pattern, we can actually match patterns from the rocks of normal and reverse. We can match that to time. And then the paleomagnetists work really closely together with the biostrat team, who sits in this room with many, many microscopes. Good morning.
Morning.
And they look at different types of fossils to get an age constraint of their of the materials they look at. But before they couldn't do that, depending on the type of fossil they look at, they need to. It's a bit bouncy today. Sorry if you're getting seasick on the other side. Before they can do that, they actually go through different stages in terms of chemicals, release these calcareous or silicate fossils. And we also have someone who is looking at dinocysts. So that requires a special sort of chemical that we handle on the ship as well. So this is kind of their world. And you can see we're quite far in the expedition now already. So we're kind of already starting to prepare to pack up samples for the science team to take home and start working on these samples with shore-based research. Yeah, and actually this is a really nice place to work, as you can see. Yeah. And we get a kind of a view of the Derya as well. Yeah, this is one of the labs on board. Yeah. Sarah, how are we doing for time?
Yeah, we're good. We can even do some questions. So there is actually another lab below. So that's the chemistry lab. But if you go down there, you're going to lose connection in the stairwell. The next one, and it's a massive chemistry lab. A lot of scientists that come on, it's better than that home institute. They're blown away, and they do microbiology down there. There's an X-ray lab to do XRD. There's an isotopes lab as well. Thin section lab. So it's a true floating laboratory. Does anyone have any questions?
And that's also where,
sorry.
And also that's where they squeeze rock samples as well. So to get interstitial waters to tease out the water geochemistry out of these rocks as well. Yeah, and the rock preparation labs, as Sarah mentioned.
Yeah, so we have a question on the chat. What dangers have you faced on the ship?
Sorry, can you repeat it, Sarah?
Where's the microphone? What dangers have you faced on the ship? I suppose the rough seas is the most dangerous part.
Yeah, the rough seas, but we have skilled ship's crew. I think one of the major dangers that maybe people don't necessarily think about before coming out here is seasickness. So it's a very, very basic thing that a lot of us get seasick, at least in the first days, depending on the seas. But yeah, people get their sea legs. So some of my co-workers who felt a little bit unwell in the first days where we first went to sea have no problems now with the storms, because we've been out here for 52 days now. We have another week to go. And it seems everybody is doing okay, considering the sea state. That's one danger. Of course, as you would have seen on the drill floor, there is a lot of heavy equipment, lots of hydraulics, a lot of things that are very loud. There is noise is another thing on the ship that is dangerous. But the science team don't go on the drill floor usually, so that's ship's crew. And safety is always the most important thing out here. So when we go out in any areas, we wear appropriate PPE. The other thing maybe that is a danger at sea is handling chemicals. So we have hydrofluoric acid here on the ship, with which we release some of the organic matter from the samples, and that can only be done in relatively calm sea state because it's a very, very dangerous acid. Yeah, but it's all being done in controlled conditions on the ship. So yeah, to minimize any risks.
Okay, thank you. Does anyone in the audience have any questions before? There's a few coming in on the chat, so I'll jump over if anyone doesn't have any questions. Okay, there's a few coming through. So apart from drilling, do you deploy any other instruments simultaneously? I could probably answer that if you.
So yeah, I mean the drill string and then the recovery of the core. But during transits, we also collect magnetic data. For example, after drilling, we send a number of sensors down. If the hole is stable, we're able to send some sensors down to measure physical properties that then can be used to inform seismic models and improve existing models. Yeah, those are the kind of measurements that we do in addition. Yeah, Sarah, anything I forgot?
Yeah. So in New Zealand, they installed some borehole observatories. Sometimes we plug the holes with corks that stay there for decades almost and collect data. So then we come back and we pull the cork back out of the hole and actually measure what was going on in the borehole that whole time. So we've got some of that stuff going on. Again, when we put the drill string down, every time we put the camera down, we put some equipment on there too. We do the conductivity, temperature, salinity tests all the way down. So that's like 6 kilometers of data. So that's actually quite significant. So that's very new. That's only about a year old, that instrument. Yeah, again, we do some seismics. We do some logging as well. So when we pull out of the hole, we put some logging equipment in. We can do many different types, borehole imaging, kind of in-hole seismics and whatnot. Yeah, we got a question?
Yeah, when you drill, how do you collect, like, is it just one single drop at each site, or can you like drill further down the same borehole multiple times? And how long does it take to collect each core?
Yeah, fantastic. Do you want me to answer this, Derya?
Sarah, can you repeat the question? It's just not carrying out here very well.
Yeah, do we come back to site and do we drill further into the hole, or is it we just drill the hole and then we abandon it kind of question?
Yeah, so we've kind of on this expedition, we usually try to do at least, like we do one hole and then we do a copy of the hole, so B hole. And if we want to re-enter a hole, let's say, you know, we drilled X meters down and then we need to abandon, like we need to leave the site because of weather, for example. We would have had to drop down a re-entry funnel. So imagine a big tripod kind of standing on the seafloor where you can then re-enter. And that seems, yeah, that of course needs accuracy. And the ship has a dynamic positioning system. So it has 12 thrusters that actually allow it to be really precise. And in certain conditions, we can then re-enter, and that's usually seas that are somewhat calmer than out there today. So sometimes IODP sites will be, after even decades, they can be re-entered to kind of continue collecting of that archive. Because as I mentioned, with time, so depth is time, and sometimes different voyages have different objectives. So for example, here on this voyage, we want to understand the Cretaceous and younger climate record, and we study that from the sedimentary record that is overlying the Agulhas Plateau. It's almost a kilometer of sediments. But then if in the future researchers were wanting to go back to the site, then if we have the re-entry funnels placed, then they could go back.
Oh, thank you. Yeah. The most famous re-entry hole is 504B. We went out there recently and we went down, and that was, I think it's like its 5th time getting drilled. So it's just getting deeper and deeper. That's one hole. It's iconic, that hole. Oh, we got a question? Yeah.
I suppose linking up to that, what is a typical depth of the hole? Like, do you go through the whole kilometre of sediments?
Yeah, so the question was, what's a typical hole? Do you go through all the sediments or do you drill ahead? I can answer that.
It again depends on a little bit the objectives of the expedition. So on this expedition, we have both soft rock and hard rock, the hard rock component. So it's a combined interest of the research team to work on both. We are actually doing different types of coring. So different types of rocks respond differently to drill methods. So on this expedition, we have done quite a bit of RCB coring through sediments where the recovery maybe isn't as great as the sedimentologists would like, but it's good enough for us to be describing continuous core, but the recovery is great for the basement. And because it's a combined mission, then there is always negotiations to be had also with the teams that work together, with the co-chiefs, and then of course operationally the co-chiefs always discuss that with the advisory board of the ship that is overseeing these, like for example Glenn and other people on the ship. So different types of coring methods depending on the objectives of each mission. And we had to sometimes actually reevaluate and then abandon a hole, start drilling a second one and wash down, where you don't actually recover core, but you wash down the sediments to then get to the basement to save some time. That can happen.
Yeah, thank you. We'll do 2 more questions. That's all we have time for. Both online, if that's okay. First from Kelly, can you take us quickly through a normal day on the JR? What is your kind of shift? What do you do off shift as well?
Yeah, so a normal day on the JR, I can only speak for myself and actually my team. So we're a night shift team. We start our day at 11:45 p.m. with a crossover in the core lab that we've just been in, quickly handing over whatever has happened on the day. And this is after breakfast at 11:30, so it takes a little time to get used to it. Then you have 2 breaks during your shift where you usually go down to the galley. So it's all around meal times and the core, of course. So if there's continuous core flow, your day passes a lot quicker. So then the entire team is working together here from the different stations. We image the core, we describe it, and then we do the first analysis. And that is usually those 12 hours a day with the short breaks in between. Then the shift ends at 12:30 after our bigger crossover with the entire science team, where we discuss, where we summarize the day's findings and get an idea also from the co-chiefs what is planned for the next 24 hours or so. This expedition has been a little bit different in the first 2 weeks. We had to operate in a COVID protocol, so a COVID mitigation protocol, which meant that we didn't really see the other shift much. So we were separating. We had staggered meal times to minimize the risk of COVID-19, and it worked. And we, after 3 weeks in total, I think we then took our masks off and now are operating like a normal expedition. After shift, I personally either read or I do yoga or go out on deck if the weather allows. There's an ice cream machine on board. That's movies. Some people watch movies. Yeah.
Some do karate.
Oh yeah, we do karate twice a week. We have a very skilled technician on board who does karate classes with us. Some people write.
Yeah, thank you. Okay, last question because I like it so much. How do you know there isn't a hollow part under the ocean floor that could drain the ocean into the interior of the Earth?
That's a tricky question. So, that's a hard one to answer. But what I can say is that these expeditions are planned many, many years, sometimes decades ahead, with lots of site survey data that precedes every expedition. So each expedition makes sure that we're not drilling into a hole. Although we sometimes have the joke that we're making holes in the bottom of the seafloor to drain the water in the ocean, which of course is not true. Yeah, so site survey data make sure, for example, that we also don't drill into any sites where there could be hydrocarbons, because of course that would be quite a major risk, that there is a source for hydrocarbons. On this expedition, there was one layer. So each expedition is prepared with lots of seismic surveys where you can survey the Earth's interior, well, the first 2 kilometers of where we're going to drill. And in this expedition, there was one site where we were expecting some black shales. So that was quite exciting. And then the organic geochemists have measured all kinds of gases, for example, to tell us of what the source rock potential of this rock would be, for example. But usually years of planning to make sure that there's no hole or no surprises, because it has to be done all very safely.
Yeah, could be a way to combat sea level rise. Thank you, Derya, and thank you, Maryalice. Thanks for joining in today. It was really good. Yeah.
Thank you.
Yeah, and greetings from JR. Yeah.
Thanks, Sarah.
See ya. Thank you.
Bye-bye.
Bye-bye.
Yeah. So I'll just